Example 1. Write down the first 5 terms of the sequence given by Tn equals 6n minus 4. Hence, express the sequence using a recurrence relation. Now this subscript n represents the position of the term. So when n equals 1, that represents the first term. N equals 2, that represents the second term. N equals 3, T3, that represents the third term, and so on. So to get the value of the first term in the sequence, we substitute n equals 1 into the formula and then evaluate it. So T1 is equal to 6 times 1 minus 4. T1 equals 2. So that's the first term of this sequence. T2, that's the second term in the sequence, is 6 times 2 minus 4. Therefore, T2 equals 8. T3, third term in the sequence, 6 times 3 minus 4. Therefore, T3 equals 14. And following the same pattern, of course, T4 is equal to 20, T5 is equal to 26, and so on. So we can see from this pattern, 2, 8, 14, 20, 26, that we can get to the next term along just by adding 6 to the current term or to the previous term. So expressing this as a recurrence relation. So that means coming up with a formula of sorts that expresses the current term in terms of the previous term or terms. So Tn, so whichever term we deem the current term, for example, let's say 14, we can get to 14 by taking the previous term and then adding 6 to it. And likewise, to get to 8, we can look at the term before, the 2, we add 6 to that, and we can get to the current term. So we can come up with a general rule called a recurrence relation. Tn, the current term, is equal to the previous term plus 6, where T1 is equal to 2. So you sort of have to have a starting point so that the sequence has to start somewhere. So we can define our starting point here, T1, so in other words, n equals 1 to 2, and then every other term sort of after that, we just take whatever the current term is or the previous term, and we just add 6 to it. Example 2. Find a non-recursive formula for Tn given the recurrence relation Tn equals Tn minus 1 plus 10, where T1 is equal to 14. So the strategy here is to write out a few terms, usually 4 or 5, to see the pattern. So T1 is equal to 14, so that represents our first term, and we get the subsequent terms by adding 10 to the previous term. So adding 10 to 14, we get 24, adding 10 to 24, we get 34, 44, and so on. So from this pattern, we can see clearly that Tn is equal to 10 times n plus 4. So for example, n equals 1, 10 times 1 is 10, but of course we need to add 4 to compensate for the difference. So we get 14, test it again with another term, say the second term. 10 times 2 is 20, plus 4 gives us 24, maybe one more for good measure. 10 times 3 is 30, 30 plus 4 is 34, and that gives us our third term. Example 3. Determine whether 300 or 400 are terms of the sequence Tn equals 7n plus 20. Now the strategy here is that we substitute 300 and 400 for Tn, and we're going to test each one of those separately. Solve for n, and if we find that n is a positive integer, that refers to the particular term in the sequence, therefore that term will be a term in that sequence, and n represents the position in that sequence. But if we get a value of n anything other than an integer, then that term is not in the sequence. So let's test Tn equals 300. So we're going to form the equation. 7n plus 20 is equal to 300. So we're just going to let Tn equals 300. Rearrange the formula and solve for n. So 7n equals 280. And dividing both sides by 7, we get n equals 40. Now, since n is an integer, in fact a positive integer at that, T40 equals 300. N equals 40, so that means that 300 represents the 40th term in this sequence. Now let's test Tn equals 400. I'm going to test it the same way. Form the equation, 7n plus 20 equals 400. Solve for n, so dividing both sides by 7, we get n equals 54 and 2/7. And that doesn't make sense as a position number. When you're talking about a position or a rank, you know, the first, second, third, fourth, it doesn't make sense to have a rank that's fractional, in fact. Now, since n is not an integer, Tn equals 400 is not a term in the sequence. Example 4. How many negative terms are there in the sequence Tn equals 12n minus 100? The strategy here is to solve this as an inequality by setting Tn less than 0. So we're interested in the values of n that represent the particular terms or the position of the terms that we're interested in, such that 12n minus 100 is less than 0. So let's set up the inequality. 12n minus 100 is less than 0. Solving for n, so 12n is less than positive 100. Dividing both sides by 12, we have n is less than 100 over 12, and 100 over 12 is just 8 1/3. So the first integer less than 8 1/3 is 8. Hence, the negative terms are from n equals 1 to n equals 8. So in other words, t1, t2, t3, all the way to the 8th term. So therefore, there are 8 negative terms in the sequence. And you can test this, of course, by substituting in, for example, n equals 1. Of course, you're going to get a negative number. Check n equals 8, since that's the highest value of n, such that 12n minus 100 is negative. 12 times 8 is 96. 96 minus 100 is negative 4. So the next term then beyond that, so n equals 9, of course that will result in a positive value there. Example 5. Find the first positive term of the sequence Tn equals 7n minus 60. The strategy here is to solve the inequality by letting Tn greater than 0, and then finding an integer value of n such that 7 times that value of n minus 60 will give you the smallest possible positive Tn. So let's set up the inequality. 7n minus 60 is greater than 0. Adding 60 to both sides, we have 7n greater than 60. Dividing both sides by 7, we have n is greater than 60 over 7, or 8 4/7. So Tn is positive for integer values of n such that n is greater than 8 4/7. So the next integer value of n greater than 8 4/7, of course, is n equals 9. And we can test that by substituting n equals 9 into the original formula. So T9, the 9th term, is equal to 7 times 9 minus 60. 7 times 9 is 63. 63 minus 60 is 3. So T9 equals 3. So therefore, the first positive term in the sequence is the 9th term, 3.